I've presented these results out of their historical order. Historically, the cut-elimination for P&O arithmetic comes first. That was proven by Gensen in the 1930s. When he showed the first version of the proof to people, it was a very different looking proof than the one we saw. When he showed this first version of the proof, there was concern, especially from Gödel, about the way induction was used in the proof. So then Gensen looked at his original proof and extracted the idea of the ordinal epsilon zero from that argument. Goodstein's theorem comes later, in the 1940s. Shortly before Gensen's work, Gödel had proven the incompleteness theorems, which said, assuming you believe that P&O arithmetic is consistent, that P&O arithmetic must be incomplete. There must be some true facts about the natural numbers which can't be proven in P&O arithmetic. The first example given by Gödel is a tricky technical encoding of a statement that roughly says this statement cannot be proven in P&O arithmetic. And the second incompleteness theorem uses an encoding of the statement P&O arithmetic is consistent. Those are interesting statements, but they're very technical. And in particular, they're encodings of statements about logic. Gensen's work led him to prove that P&O arithmetic can't do transfinite induction up to epsilon zero. That doesn't sound like a statement in the right language. Epsilon zero is an infinite ordinal, not a statement about natural numbers. But, like statements about consistency, the statement of induction up to epsilon zero can be encoded in the language of arithmetic. But Goodstein was trying to produce a statement that looked more like ordinary mathematics, but was still unprovable in P&O arithmetic. He invented hereditary base notation and proved Goodstein's theorem in the mid-1940s. The proof that Goodstein's theorem was unprovable in P&O arithmetic actually waits until Kirby and Paris in 1977. That appears to be a historical anomaly. The presentation of the arguments in these videos is very influenced by much later work, but the techniques don't really go beyond what Gensen knew how to do, so it probably could have been proven in the 40s. So Goodstein was looking at Gensen's work, looking at epsilon zero, and invented this theorem with the intent that it could only be proved using induction on epsilon zero, knowing from Gensen's work that would mean it's unprovable in P&O arithmetic. Gensen's result, the cut-elimination theorem itself, is actually much more general. Suppose I prove a for all exists statement in P&O arithmetic, or even in that PA plus theory. I prove that for every x there's a y so that 5xy holds, where phi has no quantifiers. Then, for each n, I have a proof that exists a y phi of ny holds. Then I use the results we've proven. I get a proof of exists a y phi of ny in z infinity, and then by cut elimination, I get a cut-free proof of exists a y phi of ny in z infinity. Now, z infinity is an infinitary proof system. It has this infinitely branching for all introduction rule. But there are no universal quantifiers in exists a y phi of ny. And it's a cut-free proof, so there are no universal quantifiers anywhere in the proof. So there's no opportunity for it to branch infinitely. This is actually an ordinary, finite proof of exists a y phi of ny. Furthermore, it's a constructive proof, because if you look at the structure of our cut-free proofs in z infinity, they're very explicit. There must be finitely many exists introduction rules. So if you want to know what the actual value of y is, you just look at each of these finitely many rules, look what value is being used for the exists introduction, and one of those finitely many values must be the actual value of y. So, observation 1. Suppose PA plus proves for all x there exists a y such that 5xy. Then, for each natural number n, there is a constructive proof that there exists a y such that 5ny. Second, you can go through the arguments we've given more carefully to see that the ordinal bounds don't depend on the choice of n. So, observation 2, suppose PA plus proves for all x there exists a y such that 5xy, then there is an ordinal alpha less than epsilon 0 such that for every n there's a y less than h alpha of n such that 5ny holds. That's basically how we showed the unprovability of Goodstein's theorem, but it applies to any for all exists statement. Furthermore, our proof of cut elimination is actually constructive and finitary other than the well-foundedness of epsilon 0. We didn't really use anything infinitary in our proof. We've talked about Z infinity as an infinitary proof system, so this might be surprising. But actually, Z infinity can be encoded in a finitary way. The idea is that we can replace this infinitely branching for all introduction rule with a computable version. So at a for all introduction, we have a code for a computer program, which on input n outputs a code for the deduction of the nth branch. The details of encoding all our deductions as computer programs are sort of messy and technical, but they don't really introduce any new complications. When you do that out in detail, you realize all of this is constructive. So observation 3, given a deduction in PA+ of for all x exists a y phi of xy, where phi has no quantifiers, there's actually a computer program that transforms that proof into the computer program, which takes the input n and outputs the y, making phi of xy true. So this leads to one of the branches of modern proof theory. Suppose someone has written down a proof that promises a number exists, but doesn't tell you what that number is. Maybe it's a proof by contradiction, or it uses some abstract machinery. Compactness arguments and limit arguments do this a lot. Cut-elimination tells us there should be a constructive proof, and that in principle there are mechanistic ways to find it. In practice, this is quite difficult. Journal articles aren't actually written as formal proofs in PA+. Cut-elimination is computable, but the bounds are h epsilon 0, so it's not feasibly computable. So developing and using proof transformations which are like cut-elimination but are feasible and which can be feasibly applied to real proofs is what gives the branch of proof theory known as proof mining. We only talked about cut-elimination for P&O arithmetic, but it turns out these transformations apply to many other theories as well, not just PA and PA+. In a different direction, we've talked about epsilon 0 as a transfinite ordinal, as something that seems to go beyond the natural numbers. But we can actually talk about epsilon 0 within the language of arithmetic, within the language of the natural numbers. The idea is that we can use natural numbers to code the ordinals. A very simple way to do that would be to define a function e from ordinals below epsilon 0 to the natural numbers, inductively as follows. E of 0 is 1, e of omega to the alpha 1 plus ... plus omega to the alpha n will be 2 to the e of alpha 1, 3 to the e of alpha 2, times ... the nth prime to the e of alpha n. And then, if I give you a natural number, you can figure out which ordinal it codes by just looking at its decomposition into prime factors. Obviously, not every natural number encodes an ordinal. In fact, the number 0 doesn't encode an ordinal in this scheme. But that's fine. What's important is that we can write down an arithmetic formula, a formula in the language of arithmetic which defines the set of codes of ordinals. There's a formula C epsilon 0 of x, the codes of epsilon 0, so that C epsilon 0 of n is true if and only if there's an alpha less than epsilon 0, so that n is e of alpha. And there's another formula, less than epsilon 0, so that less than epsilon 0 of nm is true exactly when n codes an ordinal less than the ordinal coded by m. That is, n is e of alpha, m is e of beta, and alpha is less than beta. And then we can actually write down the transfinite induction axiom for induction on the ordinal epsilon 0. Transfinite induction for formula phi says, suppose that for each x which codes an ordinal, if phi is true of all the codes of smaller ordinals, then phi is also true of x. Then in fact, phi is true of all the codes for ordinals. With just a little more work than we've done, we can see that P&O arithmetic can't prove transfinite induction for all formulas phi. We proved Goodstein's theorem. The only part of the proof we couldn't easily carry out in P&O arithmetic is the transfinite induction up to epsilon 0. So if P&O arithmetic could prove the transfinite induction, it could prove Goodstein's theorem, which, as we've seen, P&O arithmetic can't do. This is what Gensen proved, that transfinite induction up to epsilon 0 was not provable in P&O arithmetic. But P&O arithmetic can prove infinite induction for any smaller ordinal. Suppose n is a code for an ordinal, then P&O arithmetic does prove the formula saying that we have transfinite induction up to n. Epsilon 0 is the smallest ordinal, with the property that P&O arithmetic does not prove transfinite induction up to epsilon 0. To say that carefully, you run into some technicalities about coding. I picked one encoding of epsilon 0. There are other ways to encode it that you might worry would lead to different outcomes. The exact thing to say turns out to be epsilon 0 is the smallest ordinal such that no matter how you encode it, P&O arithmetic can't prove transfinite induction. For every alpha less than epsilon 0, there is some way to encode it so that P&O arithmetic proves transfinite induction up to alpha. And that leads to the question, what about theories that are stronger or weaker than P&O arithmetic? For this to make sense, let's talk about theories of arithmetic. That means a theory that can talk about the natural numbers. For that to make sense, it has to contain some basic facts so we know that what we're talking about is the natural numbers and not the reals or something. To make that formal, we would pick some weak set of axioms, a lot weaker than P&O arithmetic, and say that we only want to consider theories which still contain these basic axioms. But also, we're fine with theories that talk about things in addition to the natural numbers. For example, set theory is fine. ZFC can construct the natural numbers and talk about them. We don't care that it can also talk about other objects. So let's say we have a general theory T of arithmetic, something that encodes the natural numbers in a way that proves these basic axioms. Then there is some least ordinal lambda with the property that, for every computable encoding of lambda, T cannot prove transfinite induction up to lambda. And we call this the proof-theoretic ordinal of T. The proof-theoretic ordinal of a computable theory is always going to be computable, so it's a countable ordinal below omega 1ck, which is the name of the first ordinal that has no computable representation. The proof-theoretic ordinal of P&O arithmetic is epsilon 0, and we can then try to measure the proof-theoretic ordinals of other theories. For instance, there are interesting fragments of P&O arithmetic, especially theories where we weaken the induction axiom, which have smaller proof-theoretic ordinals, things like omega to the omega to the omega, or omega to the omega to the omega to the omega. And in the other direction, people have identified the ordinals of stronger theories. These ordinals get much more complicated to describe as the theory gets stronger. Theories are not linearly ordered, but ordinals are. So the proof-theoretic ordinal is one way to measure the strength of a theory. It doesn't measure everything about a theory. Different theories can have the same ordinal, but it turns out to be one useful measurement. In particular, it's measuring some kind of finitary content of a theory. The proof-theoretic ordinal is really about which for all exist statements are provable in a theory. So ordinal analysis is the branch of proof theory focused on examining the ordinals of various theories. One last way of looking at cut-elimination. We've been talking about theories of arithmetic, where incompleteness is a dominant theme. But for other logical systems, for instance, a lot of modal logics, it's reasonable to have a complete proof system. And cut-elimination gives an approach to getting a handle on these sorts of logics. What we did for arithmetic was produce a special deduction system with these nicely paired rules, which made it possible to prove cut-elimination. And that idea leads to structural proof theory, investigating other logics by trying to find a system of deductions in which all proofs can be transformed into particularly nice proofs, and then learning something about what's provable or disprovable in this logic by examining the structure of the nice proofs, which, like our cut-free proofs, may be much easier to understand.